Tonight we're going to talk about the exciting world of grounding and bonding. That I'll just put you on the edge of your seats, everybody. But it's an important thing that we discuss as home inspectors, and it's a broad topic. We're going to get into a lot of it. We could talk for 8 hours on it, which we're not tonight, but try to condense this slideshow down somewhat to, well, my slides aren't advancing. Okay. Kind of condensed it down to fit this 1 hour format. This is my email address and my website link. If anyone wants to copy my email address, I invite people when I do seminars all over the country to, if they have questions, contact me, comments, whatever, phone calls. I always try to get back to people. I have a group of neat guys that I've talked with over time discussing electrical issues. So if you want to contact me at any time, I'll try to get back to you. Leave me a message and I'll get back to you. Okay, if everybody's got that, we're going to move right along. And if you don't, I can come back to it. Okay, what is grounding and bonding? It's perhaps the most misunderstood and confusing topics to grasp for many home inspectors and also a lot of electricians. Grounding, and bonding will be defined to simplify and clarify the differences in proper installation practices. Potential hazards of parallel paths of grounded and grounding conductors on the load side of the service of the equipment will be explained. So we're going to go over a lot of things here tonight in a short period of time. So, and I think I told Hollis yesterday, if anyone has questions, I will be glad to answer them as we go, as they're presented to me. Okay.
Yeah, put questions in the chat and Sean will pose them to the speaker.
Okay. Inspecting the grounding system. That's an important part of a home inspection, but there are limitations. We're going to discuss that. Okay, what does the ASHI standard of practice say about this procedure? It says the inspector shall inspect the service grounding. Now, my home state of Tennessee, the standards are pretty similar, and I think it just said we shall inspect the grounding equipment. That's kind of a general statement, but here's my opinion on that. It's impossible for a home inspector to fully inspect the grounding system of a home or a building in almost all cases. The reason for that, most of it is below ground. And I say that in that ground rods are supposed to be driven to a certain depth. Unless you've got a shovel or a backhoe, you're not going to confirm that it's proper. So even home inspectors aside, I do some code compliance inspections, have in the past, and don't do many, but from time to time. And I did one last week for Metro Nashville, and the same situation. I couldn't confirm that the ground rod was 8 feet in the ground because it was a retrofit on an older house. They did drive a new ground rod, but I could see it, and it was properly clamped. Grounded electrode conductor was proper, so that's what I had to go on. So just keep that in mind. Don't put in your reports that a statement that the grounding system is perfect and everything is right, because you really don't know that. So what do you do? Okay, here's another statement from the ASHI standard of practice. The inspector is not required to determine the condition of systems and components that are not readily accessible. A lot of the grounding electrode system in a home is not readily accessible. Unless you're there when it's being installed, you're not going to be able to inspect and confirm everything is as it should be. So that's not a real big deal. I mean, we're generalists as home inspectors. As an electrical inspector, you go a little more in depth, but even then you're limited in what you can see and what you can confirm. So what you should do is inspect and report on what is visible and what is accessible. Put that in your report. I typically had a statement, blank statement in mind that generally around here on existing homes, of course, you wouldn't, a lot of them older, the ground rod has gotten subsurface. You can't see it. You see an equipment grounding conductor going down into the earth. I would have a blank statement that the grounding electrode conductor was observed, it was inspected, it was proper size, and the ground rod was not visible. Or if it was, only the top of the ground rod and the connection was visible. I didn't make a statement that the home was properly grounded in all cases. Okay, we're not going to get into codes. We're going to touch just a little bit on it, but this is not a code class, but just for reference, I think, if I'm not mistaken, a lot of you guys are in Virginia, and I don't think you can even mention codes in a report in Virginia. I think that's against the standards, if I'm not mistaken. I think I read that somewhere. So, and that's okay. But if, you know, the conversation comes up anyway among home inspectors, like it or not, but this is the article that covers grounding and bonding in National Electric Code, Article 250. And there's a lot of information in that article. A lot of it can be confusing. So we're going to go over some definitions and so on to try to simplify some of that verbiage to help you understand what it's talking about. Okay, here's some basic definitions. Grounding and grounded. That's connecting or connected. And these definitions actually come out of Article 100 of the National Electric Code. So I didn't write these. These are smart people wrote this. So we'll go by what they said. It's grounding and grounded is connecting or connected to ground or to a conductor that extends the ground connection. Okay, that's kind of a complicated way of saying you're sticking something in the dirt and connecting to it. Okay. Bonding and bonded is connecting or connected to establish electrical continuity and conductivity. Okay, let's think about that for a minute. If you're tying a bunch of conductive equipment together through a conductor, whatever it be, then you're bonding. There are proper ways to do that, and we'll talk about that. But it's basically putting everything in contact together to establish electrical continuity and put it all at the same voltage potential. That's the main important thing. Okay, here's a ground rod connection. This is basically what, around in my parts, this is about all we see, if we even see that. Most of the time that gets covered up. But this is an acorn clamp with a ground electrode conductor going into the acorn clamp to the top of a driven, looks like probably a copper ground rod. There is a proper way to do that. Sometimes you'll see that equipment grounding conductor on the bolt set screw side. That's improper. This one is correct. It goes in that little V-shaped end of the acorn clamp. That's the proper way to do that. These are not allowed for double taps. If you can run more than one conductor to that rod, but it requires another acorn clamp or suitable clamp for the other conductor. That's a mistake a lot of electricians make, and they fail inspections. They pay another, whatever the fee is, $40, $50 to go back out there and put another little $5 acorn clamp on there that they didn't do. They'll fail you on that if you don't do that. Okay. Shout out to Douglas Hanson and Skip Walker for allowing me to use some of their wonderful, I mean, these are great illustrations that they have in the CodeCheck Electrical. They've just revised that, and it's a great reference, and they've allowed me to use some of these in some of my presentations. This one is this is an acorn clamp, and it's showing just an illustration of what we just looked at. You can see that the conductor is on the proper side of this clamp. And Douglas has made a comment there, do not terminate on the bolt side. Conductors number 6 and larger, if they closely follow the building contour, they don't need additional protection from damage, physical damage. Weed eaters are terrible on these things. People beat them up. You wouldn't think over time, I mean, that the nylon cord would cause damage, but over time it can beat them up, loosen them up. So they should be protected when they're exposed to physical damage. Okay.
Hey, Mike,
Yes.
should that clamp be above ground or is it okay to be below ground? Because I've seen mostly it's below ground.
It can be below ground if the clamp is listed for direct burial, and they'll have that marking on the clamp, and most of these are. As far as being above ground, it's what the code says is the rods are typically 8 feet long, and it says 8 feet supposed to be in the ground. So if it's sticking up much more than 3 or 4 inches, then they could call you out on that and say you don't have 8 feet in the ground. A lot of guys in real tight jurisdictions will buy the 10-foot ground rods, and but it can be above ground, and it can be below ground. But if it's below ground, the clamp has to be listed for direct burial.
All right, thanks.
Did that answer your question?
Yes, thanks.
Okay.
Let's remember to put our questions in the chat.
This is a UFR or concrete encased electrode. This is the rebar steel coming up out of the foundation footing that they bring up, and that's something that if it in newer construction, if it's present, that has to be included in the grounding electrode system. You have to tie that to the system. It can be the only electrode. I'm gonna back up one step, and I may have a slide later, and I apologize if I'm redundant in this, but a ground rod, a single ground rod, has to be proven to have less than 25 ohms to earth, and there's a test they do for that. The test can be fairly expensive for an inspector to check it out. So what most of them, if they're driving rods, what typically electricians do, they just drive 2 rods. They have to be at least 6 feet apart and bonded together. And that's a lot cheaper than going through the test. Now, if you drive that second rod, you don't have to prove anything. They don't do any tests. It may still not be less than 25 ohms, but they don't check it. That's just a provision that's allowed for 2 rods. Going back to the UFR, that can be the sole electrode. It doesn't require a supplemental rod per code. Well, let me back up on that. It doesn't require, if one is present, like if there's an underground water pipe, it has to be tied to the system. It's not the sole electrode, but it has to be included and bonded to the grounding electrode system. We'll talk a little bit more about that here in a minute. But that's a UFR, and they generally bring them up like this in garages, crawl spaces, whatever, where they're accessible. They have to be accessible. Well,
hey, Mike.
Yes.
There's a question. Is that box thing required?
The box, it has to be accessible if it's above ground. Now, it can be completely encased in the footing if it has a listed clamp for that. They make a clamp that can be encased in concrete. It can be buried in that. In that case, of course, it's not accessible. But if it's brought up out of the footing, it has to be accessible for the clamp attachment, of course, and for inspection.
So a follow-up to that. So a grounding rod encased in concrete. Sorry for the feedback. A grounding rod encased in concrete, such as a walkway, is not a UFR. Is that right?
That's right. Well, if a UFR has to be 20 feet, a 20-foot length encased in the concrete, 20-foot minimum. And it doesn't have to be one continuous, one single piece. It can be tied together with the steel ties to make 20 feet, but it has to have a minimum of 20 feet in the concrete. It can also be a number 4 bare copper conductor, like you're seeing this grounding electrode conductor similar to that coming to that rod. It can be that can be the UFR in the concrete. But now you ask, could a ground rod be used? I suppose it could, but who's going to use a ground rod in a footing when rebar is a whole lot cheaper? I mean, they're going to use what's there. So it's using the foundation steel for the grounding electrode. Okay, we're going to talk a little bit about bonding here. This is a panel enclosure bond. This is actually service equipment. It's a close-up. You can't tell that, but I remember this. I mean, I know what this panel is. This jumper that I've got circled here is actually bonding the enclosure, the metal can, the cabinet, and it's bonding the neutral, which is coming into this terminal bar above that you can't see in the picture, but the service neutral is coming into a top lug there. So it's doing two things. It's bonding the enclosure and it's bonding the neutral to the enclosure and to these equipment grounding conductors. And that's probably being aluminum, that's probably a water pipe bond, that's solid one. So that's a listed main bonding jumper. This is probably an Eaton panel. That's kind of their style. This is one of square D, the green screw up at the right. That is the main bonding jumper in this panel. Different manufacturers have different methods of their listed bonding techniques. That screw is bonding the neutral bar there at the top that you're seeing all the way through, goes through that plastic back plane, and it's screwed into the tapped hole that's in the metal can. You don't want to see sheet metal screws or anything like that. That's a listed screw that goes in there. Now, if you want to use this panel as a sub panel, that screw comes out and some changing goes on as far as where your equipment grounds and your neutrals are connected. We'll get into that in a little bit, but that's a main bonding jumper, bonding screw, but it's code calls it a main bonding jumper.
Hey, Mike.
Yes.
Someone has seen UFR ground copper coming out of the floor, presumably attached to the rebar and the footing. Does it need to be welded before it's buried in that case?
No, they make a clamp that's listed for encasement in concrete, and it has to be listed for that. So it can be clamped and then concrete poured over it. So no, it doesn't have to be welded. Now there's some, I think it's called exothermic welding that's suitable. There's certain irreversible crimp conductors that can be, crimp connectors that can be used, but it can be a clamp.
And then a follow-up to that is, are they removing the requirement that it's visible or accessible?
For a UFR?
Right, the connection.
Are they removing that requirement? You're talking about is code removing that requirement?
Yeah, is the requirement for that UFR connection being accessible going away? Have you heard?
No.
Okay.
No, I have not heard that.
Okay.
And I would doubt that seriously, because I mean, it's an inspection point for an enforcement, a code enforcer.
Yeah, and I think it goes back to the listing, like you're saying. If the clamp is listed to be inaccessible, then it's fine. If it
Right.
if it has to be accessible, then it has to be accessible.
Yes. And some local jurisdictions, they could go a step above and say, no, we don't want it. We want to be able to see it. And they may require it to have an amendment and say, I want it above grade that I can see the connection. That's something they can do.
Good point.
Okay, is bonding allowed at sub panels? This gets discussed a lot and is a confusing point with a lot of inspectors. I hear some discussion sometime where the home inspectors say, you do not bond a sub panel. Well, that's an incomplete statement. All metal enclosures have to be bonded. And if it's a metal sub panel, that sub panel has to be bonded. But the neutral does not get bonded in the sub panel. So that's two different means of bonding. You bond the metal can always. Any metallic enclosure gets bonded. But the neutral does not get bonded to that panel like we showed in the previous slides as it does in the service equipment. That's the difference. So understand that when you just say you can't bond a sub panel, well, you have to bond a sub panel as far as to keep that continuity of the metal connected to the other equipment in the home. Okay, here's another one of the code check slides. It's a good illustration. This is a service equipment panel. I don't know if you can you guys see my cursor if I move it around?
Yes.
Okay. All right. This is the service neutral coming in to this bar. This bar is elevated off of the can. So it's, some people call it floating. I guess that's a good term. This is the bonding jumper that ties this, and this screw is tapped into the back of the can like we talked about before. This is a tie bar going across to this other terminal. This terminal is actually touching the can. So if I'll show you a slide of a sub panel in a minute. If it's a sub panel, then this one's bonded. Okay. Now in this panel, the neutrals and equipment grounding conductors are required to be bonded together. They're all tied together because this is a service equipment panel. So you can tie the neutrals and the equipment grounds to either one of these bars in this panel. That confuses a lot of people. They think, well, all the equipment grounds got to go here and all the neutrals got to go here. In this situation, it's all tied together and it's allowed. You can't double them up, neutrals. You can the equipment grounds, but as far as two on one terminal, but you can have some of your neutrals over here, some of them over here, some of your equipment grounds over here, some of them over here. Now for neatness and simplicity, a lot of times the electricians will put all the equipment grounds together, all the neutrals together. Makes it look better. Another thing I'm going to point out in here, this neutral conductor is re-identified with white tape. It's a black conductor. It's a bigger wire. That is allowed on number 4 and larger wires. You cannot re-identify a neutral or an equipment ground on smaller wires. Like you can't, you see it done sometimes. Somebody will have a lot of black THWN and they'll pull it in 3 times and they'll tape up one as white, one green, and then the black hot. That's not allowed for smaller conductor wires. I found that out not too long ago. I had done that for years, never, and doing a boat dock installation with a neighbor, and it got called out, and I looked it up, and it's been there forever. But that's just something to know, and that's not that big a deal with home inspectors, but you'll see it sometimes, the smaller gauge wires. So just remember that anything smaller than a number 4 for equipment grounds and neutrals cannot be re-identified with tape or markings. Okay, we're going to look at a sub panel now. This is basically the same panel without a main breaker. This is a main lug panel now. Now you see the neutral, I mean the main bonding jumper has been removed from this terminal here. So now this one is a gray wire, it doesn't have the white tape on it, but this is your service neutral. These are your branch circuit neutrals, and they're all over here. Your equipment grounds go on this side. Now they have to be separated. This is a 4-wire feed. This is a service panel. This was a 3-wire feed. That's all you need in the service panel. The neutral takes care of through bonding of the path back to the transformer for the equipment grounding in event of a fault. So back to the sub panel. It says you don't bond the neutral in the sub panel. This is now the neutral bar for neutrals only. The equipment grounding bar for equipment grounding conductors only. They're separated in the sub panel. Like I say, it's a 4-wire feed, which you're going to see in a sub panel. I think I've got another slide. I want to discuss something on this same subject here. Okay. Where do the wires go? This is a picture of actually a compliance inspection I did last week, a brand new installation. And I was looking for one of these to kind of get this point across. All right. The metal enclosure can be used for continuity for the equipment grounding conductors, but not for the neutrals. And what that means is this bar right here is bonded. It's directly contacting the panel. So it's connected to it. This is, like I say, this is the main service panel, 3-wire feed. No equipment ground feeder for this because it doesn't need it. Now, these equipment grounds can be on this bar and they can be on this bar or that bar. Equipment grounds can use the continuity, since this is bonded right here. This ties all this to the metal can. This can use the metal can as a conductor for these equipment grounds. It cannot be used for the neutral. The neutral has to go on the neutral bar, which has a tie bar here going to the other. So the neutral has to go through here. You can't put a neutral here and let the continuity of this metal can supply the continuity to this neutral on this bar. I'm probably confusing people, but basically it's that rule was changed, I think, in 99, maybe. I don't know, but that's not important. You just, and that confuses a lot of people because they'll see on the service panel, like I say, see them mixed up. They'll see equipment grounds and neutrals all down through here, and they may see all equipment grounds here, some neutrals and equipment grounds here, and they say, and I have guys call me and they call it out and say, these equipment grounds aren't supposed to be on the neutral bar. And the service panel, they're fine. It's bonded. It's the same as that.
Hey,
Everybody
Mike.
understand that? Yes.
When I see a green grounding screw present in a sub panel, I call it out as a potential bonding issue. Is that right?
When you see a green grounding screw in a sub panel,
Correct.
yes. A lot of times they'll put that in, this green screw up here in a sub panel. It won't be fully engaged and it won't be making contact with the panel. And I've had some discussions with electricians in the past. I say, just take it out. I mean, you know, somebody sees it and says, well, that's not tight, and they tighten it up, and then you just bonded a sub panel. So I say completely remove them.
Is there a way to know if it's making contact with the box?
Well, you could ohm it out, but I mean, that's just a no-brainer to me. And a sub panel there's no purpose for it to be sitting there. Take it out, put it in your pocket, put it in your toolbox, and use it on the next service panel when you lose the bonding screw. It shouldn't even be in that sub panel.
And then Dan made a clarification. He said equipment ground wires are non-current carrying conductors. So passing through the metal case is not a problem.
Right. Well, when you say they're not current carrying conductors, they're not current carrying conductors when everything is good. You certainly want them to carry current when there's a fault because that's what they're there for. Does that make sense? They don't carry current in a normal situation. If everything is there's no faults. But if this you get something against this case, like this hot wire, a whisker comes off here and energizes this case, then the equipment, or that's a bad example. If a branch circuit, this equipment ground carries the current back to the neutral, back to the transformer to complete the circuit and trip the breaker. It's got to have that complete loop to trip a breaker or blow a fuse. So they do carry current when there's a fault, and that's why there's size requirements for equipment grounds, just like there are other conductors, depending on the amp rating of what they're protecting. Okay, here's a CPVC pipe that's bonded. That's kind of being safe there, but it's ridiculous. It's not needed. It's somebody just, I guess he just said, I've seen water heaters bonded before, so I'm gonna bond this one. So the water heater is already bonded with the equipment ground for the branch circuit to it. So that's kind of funny. Another home inspector sent me that. He said, have you ever seen this where they bonded the PVC? Okay, water pipe bond connection. This is this is different from the grounding. Let's say you've got a house that's older house that's all metal piping, copper or galvanized back in the day. That's all your distribution piping in the house. And the service line has been changed to PVC or PEX, more likely PEX. The water piping in the house still has to be bonded, because if an energized wire gets on that, it electrifies your distribution plumbing. So this is a water pipe bond. You'll see this one is a aluminum. I didn't mention it a while ago, but your grounding electroconductors typically you're going to see are copper, because the code, you can use aluminum, but it can't be within 18 inches of the ground. So people don't use it. That's kind of hard to do, to go to the ground rod like we showed in the pictures earlier and stay 18 inches away. So they typically have the equipment grounding, the grounding electroconductor, GEC, is generally copper. Now this is aluminum, this is a water pipe bond, and that's fine. It goes back to the service panel, and it can tie into the grounding electrode system at any point to bond that water pipe. Okay, here's another code check, and this is something that you very seldom see. It's supposed to be done is scraping the paint where you make a connection. If you add a ground bar, an add-on ground bar to us, let's say you got a sub panel, didn't have a equipment grounding bar, you can buy those ground bar kits and put them in there. They have tapped holes made for them. And I'm guilty of this. I've installed them and didn't scrape the paint, but you're supposed to scrape that paint to get good continuity, because that paint can be an insulator. Okay, so to be grounded, there's got to be a direct connection to the earth. To be bonded, there must be a direct connection to another conductive device or material. Both of these connections are done by design, and unintentional grounding and bonding can be present in certain situations that cause faults and hazards. We're going to look at some of those in a minute. The main purpose of the grounding electrode system is to limit voltage from lightning and power surges, and to direct that potentially dangerous energy to earth. Bonding is done to connect the electrical equipment to keep all bonded items at an equal voltage potential and to protect the electric shock from electric shock. Equipment grounding system provides a path back to the power source through an overcurrent device that will de-energize the circuit in the event of a fault on any of the bonded equipment. That's what we were talking about a minute ago. That's what the equipment grounds do.
Hey, Mike.
Yes.
Those bus bars you were talking about, do they have to be rated by the manufacturer to be used in those panels?
Yes. Yes, they should be listed for that panel, and they make the ones that come with it. I mean, they're going to come with the panel, but if you have to add a equipment grounding bus, yeah, it should be listed for that panel. And they make them. All the major manufacturers, you can buy them mostly at Home Depot and Lowe's. They've got them on the shelf up there usually.
Anything that goes in there, right?
Yeah,
has to be rated. Yep.
Right. Okay, here's some common myths and misconceptions. The grounding system at home protects against electrocution. We just said it's basically there for power surges and lightning strikes. That's the grounding system. GFCIs must be grounded to provide protection. Well, if you've done many home inspections, you've seen a lot of GFCIs on older houses with no equipment grounds, and they work. They protect without being grounded. They don't ground. It's still not grounded, but they protect for shock. They're for electrocution protection, protect people. Okay, neutrals and grounding conductors are harmless to people. Very untrue, very untrue. Neutrals carry current by design. If you've got a 120 volt, 20 amp circuit and it's got a 10 amp load on it, 10 amps is going to be on that hot conductor and 10 amps is going to be on that neutral conductor coming back. It's going to be equal. If they're not equal, then you've got a problem. That's where GFCIs come in. That's what it's looking at, equal current on the hot and the neutral. And if that gets unbalanced by more than 5 milliamps, it trips the GFCI. So I've actually seen unfortunately, a electrical presentation for home inspectors where the instructor repeated 3 different times, neutrals are not current carrying conductors. Nothing further from the truth. Okay, electrical systems must be grounded to work properly. That's a myth too. When I was working in industrial at Ford, we had ungrounded 3-phase delta systems. That was done intentionally for critical circuits, power circuits, where if one, you have a lot of water, a lot of problems in manufacturing and big industrial plants, and things get grounded quite often. If one phase gets grounded, it doesn't shut you down. It gives you a warning, and you can troubleshoot it and repair it at downtime, but it does not shut you down. So their electrical system can work without a ground. Neutrals do not carry current, like I just discussed. That's not true. And the earth is a good conductor. Not true also. It's a high resistance, but it is a conductor. Equipment grounding conductors. A conductive path used to carry ground fault current and to connect the normally current carrying metal parts of equipment together. So I'm going to go through this next slide quickly to continue with this. Okay, by that description, we see that the equipment ground has at least two purposes: as a design fault current path and to bond conductive equipment. And this is, yes, I said bond. This is where some confusion can come in. Although we refer to these conductors as grounds and grounding wires and equipment grounds, they're also bonding conductors. That's what they're doing from panel to panel. You see a feeder equipment ground going from a service panel to the sub panel downstream. It's bonding those two equipments together and providing a path for fault current. They can be wires, they can be metal raceways between panels and enclosures and boxes. And the origin of it is always at service equipment, where it's connected to the service neutral and the grounding electrode conductor, or both. When I say that it can be raceways, metal flex can be used as a equipment ground, but not more than 6 feet. Metallic seal type flex, not more than 6 feet, but rigid, thin wall, intermediate metal conduit can all be used as equipment grounds. And sometimes it is. You'll see a panel sometimes you don't see, you think something's wrong, and you say, well, I don't see an equipment ground feeding this panel. And then you look a little closer and it's got metal conduit, and that's being used as the equipment ground. Okay, we just said that. I'm watching my time here, guys. I apologize if I'm going too fast, but I'd like to get through as many of these slides as I can. Okay, this is bonding requirement for boxes. This is just, I'm sure a lot of you guys do some pre-drywall inspections. This is really when only time you're going to see this, when the boxes are all in and the wires are pulled in. Actually, and this is a code thing, so I wouldn't worry too much about it, but actually the equipment grounds are supposed to be made up in these boxes at the rough end stage. Like I say, I did a compliance inspection last week and that wasn't done. We kind of let them slide on it, just told them to hook them up, but it should be, well, sorry, wrapped together like here, and then this will attach to the equipment ground screw on the receptacle when it's installed, but they're supposed to be made up at the rough end stage for that inspection. Okay, here's a typical little sub panel that's, you see where it's got 3 2-pole breakers in. It's feeding some kind of equipment, no 120 volt loads, no neutrals. So it's just got a equipment grounding feeder here coming in, but there's something missing here. That's where the bonding screw goes. That's what I was talking about earlier. All metal enclosures must be bonded. There's no neutral even involved in this because this is for air conditioning loads, probably. That's what I'm assuming. And this has even got the little silver tape back there showing you where it goes. This is a tapped hole through here. That green screw we took out of that other sub panel, we put in our pocket. Now we're going to put it in here because we didn't have one. We're going to fix this. So look at this. This is a very common problem with HVAC sub panels. When they use a little sub panel for the HVAC equipment, pick on the HVAC guys here a little bit. They're terrible about not bonding that bar, because this panel could be used, this could be used as a neutral bar in a different situation. That's why it's floating. In this case, there's no neutral and that should be bonding it, but this bar is not contacting this can. So all this is not bonded. This particular panel could become energized and there's no path to clear a fault on it. I'm showing a measurement. This is another one, and I'm reading here from this lug, hot lug, to the ground lug, and I'm getting 122 volts as I should. I'm reading to the equipment ground that's coming in here. Same panel. Now I go from the same hot lug and I go to the metal can. This is just a phantom voltage. There's no voltage here. That's telling me, I mean, I could see it visually because this is floating, lifted off of the can. This is showing through a meter that this this cabinet is not bonded. That should have the same potential as when I put the other probe here. That's showing that there's a voltage difference between that, and that's dangerous. You see it a lot. I mean, a lot.
Hey, Mike.
Yes.
That was a great explanation just now. Thank you. One question, can the conduit be used as the fourth conductor in a subpanel?
Yes. It can. If it's what I mentioned earlier, if it's rigid, EMT, intermediate, and if it's properly connected together, yes, it can. And it often is. Let's see. Okay, we discussed that. The grounding electrode conductor, GEC, that's grounding electrode conductor, is connected to the system neutral. This can be done at the service equipment panel, the meter base, or at the load end of the overhead service drop. I've got a graphic showing that. You can make that grounding electrode connection at any of these three places. You're not going to see it here too often, but it can be here. It can be connected there, and then it's not going to just drop out of the sky, but it's going to follow the building down and go to the ground rod. In my jurisdictions where I live, our utilities require that the grounding electrode conductor land in the meter base. That's not a national electric code allows these three, but the utility says we want all the equipment, the grounding electrode conductors to land in the meter base. A lot of jurisdictions typically have them in the service equipment. They can be at any one of those three places. Here's one. It's actually, this is the equipment. I mean, I keep grounding electrode conductor, I apologize, going to the ground rod right here from the meter base. This is a back-to-back. This right on the inside wall of this basement is a service panel. In some jurisdictions, it could have gone in there, or in any jurisdiction, but like I say, our utility said it's got to go here. They won't give you a service release if it does not land in there. Okay, all electrodes that are present must be bonded together to form the system. They can be driven rods, underground water pipe, concrete encased electrode, UFR, ground ranger plates, and structural steel if present. So let's talk about that a little bit. Underground metal gas pipes are not allowed to be part of the GES. They can be bonded and should be bonded, but they're not part of the grounding electrode system. Different situation. Bonding is different from them being part of the grounding electrode system. All right, metal water pipes must be supplemented by another electrode. All the older houses we used to see, that was the main grounding source, was the underground metal water pipes, and it was a great ground rod. But as plastic pipe became prevalent, code started realizing that's going to start getting replaced, which loses the grounding electrodes. So they started saying that it must be supplemented by another electrode. Start driving ground rods. The water pipe can, when I said earlier that a driven rod had to prove that it was less than 25 ohms to the earth, and if you need a second rod where it's not, they won't allow the water pipe to be that supplement. Even if you got a metal water pipe, you tie to it and then you drive two ground rods, you still got to have two ground rods. Grounded conductor. system or circuit conductor that is intentionally grounded. Okay, the neutral in a standard residential system is a grounded conductor. Not all grounded conductors are neutrals. That's why the code doesn't call, they don't just refer generally to all of them as neutrals. They call them grounded conductors. There are systems in industrial. You're not going to see it unless you're doing commercial inspections, but where a phase conductor is intentionally grounded, and they're not neutrals. They're a phase conductor. They have equal voltage to the other two phase conductors. So, but for our purposes in home inspections and what you're going to see, the neutral is the grounded conductor. That's what we're going to call it. Okay, although the neutral, the equipment grounding conductor and grounding electroconductor are all grounded, they have different and specific functions. If you don't remember anything else from what we're talking about tonight, remember and understand this. In a normally operating electrical system, the neutral carries current by design. The equipment grounding conductor and the grounding electroconductor only carry current in the event of a ground fault or a fault from outside sources. Lightning can put current on it, or improper load side bond. That can put current on those conductors that are not intended to carry current except in a fault. But a neutral, it carries it by design. Okay, here's a service panel. We'll just kind of look at a few things here. This is the service neutral coming in. This is the bonding jumper. It's not green in this old panel, but that's the bonding jumper, which is tying the neutral to the can, tie bar going over to this other floating bar. You see equipment grounds and neutrals mixed up on here. That's allowed here too. See some that are double tapped. That's not allowed with ground in the neutral, but they can be on either side like I was talking about earlier. This is probably the grounding electrode conductor. This is a equipment grounding feeder to probably a higher amperage appliance circuit. This aluminum, I'm assuming, is probably a water pipe bond, and it's double tapped here where it shouldn't be, but that's what these things are. That's an older panel. Pull out fuse. Yes.
My quick question.
Okay.
Why can you double up ground wires in a bus bar, but not neutrals?
Probably the main reason for that is, like we talked about earlier, they're not carrying current unless they're the fault. So they're not getting heated up, cooled off, heated up, cooled off like a neutral is. Neutrals being energized, de-energized. So it needs to have a good, secure, single termination where the equipment grounds are. And I wouldn't be surprised to see more stringent in the future where they may come out and they may not allow doubling up the equipment grounds in the future. I don't know, but that's why it's not under load in a normal situation like a neutral is.
Now let's try to remember to put our questions in the chat, please.
Okay, here's an old panel. This was I think 1969 house I did a few years ago. This is the main service panel, and the tape is losing its stickiness, but there's the bonding screw that came with it when they shipped it, and they never put it in. It's still hanging on the tape, and that's the way a lot of suppliers will send the panels. If you're going to use it as a sub panel or a service panel, then it's up to you whether you put the neutral bus. This one was never bonded in all those years. It's still hanging on the wall of that panel. Well, it's not now because this was a home inspection I did, and I had it bonded. But that was been there since 1969. Intersystem bonding. This is a requirement that came about, I'm not sure, a few years back, 2002 maybe. This is for the cable guy, the phone guy, where they used to put the little clamps on the cabinet. And they would, the worst thing they would do, I had a phone guy that he would drive a ground rod on the other side of the house and tie his phone to it. That's terrible. That gives gives a voltage difference in grounding systems in the same house. So they required this, and this is where they can put their equipment And this is the grounding electroconductor that goes through this. It's not broken in here. It goes through. It can't be spliced, and it ties through there, and then their stuff, it gets bonded to the grounding electrode system by this termination. This is a riser, metal conduit riser that is broken loose from the threaded hub that goes into the top of this meter base, and that's what bonded that conduit. So it doesn't have a good bond. I mean, that hub is what bonded it to the equipment. So that's a dangerous deal when that pulls loose. Most of them you're seeing these days are using PVC, but we'll touch on CSST. We're not going to go into detail on that. I'm sure you guys are aware of that. This is the link for the bulletin. It's been required to bond the CSST and International Fuel Gas Code and IRC since the 2009 editions, and it's required by manufacturers. It is not required by the NEC as far as the specific bonding requirements with the number 6 conductor, so on and so forth, that the others require. My opinion, people ask about the counter strike, the track pipe, the black insulated CSST. In my opinion, it's best practice to bond all of it. The manufacturers, it's okay. I mean, the manufacturers have it listed as the conductor is in that insulation, but I just it's not that big a deal. I require to bond all of it, and there's not really any exception in the IRC that says that that they're exempt from that. Of course, you can have that argument, manufacturer's specs as opposed to code. But anyway, if you can look that up, we're not going to go into detail on CSST tonight. This is a metal boat dock frame that's properly bonded. This was required, this bonding jumper, this green bonding jumper was required here to tie. It goes back to the, I apologize, goes back to the sub panel that's feeding this boat dock, and then it's jumpered here to the steel frame dock. This beam clamp, and the reason it's done this is a metal conduit, and it's got seal tight on each end, so it's floating out here, it's isolated. So this had to be bonded to this metal dock in case it were to become energized. And the beam clamp that attaches the conduit to the steel is not a listed bonding connection. So this jumper had to be put on there. If you live around lake homes and stuff, if you look at boat docks, they've got a particular set of requirements. I live on a lake up here, and I've wired probably 50 or 60 residential boat docks. So this is one that I was called out on. Actually, a neighbor across the lake from me called me and said they were swimming summer before last around their dock, and when they touched the dock to get out, they felt a tingle. And what had happened, this was an old dock that was not properly bonded. This is the seal tight going out to the lights and plugs on the dock, and the water came up, had a little flood, it shifted this steel over, and it crushed this seal tight enough to cut into the hot wire and energize all this steel. It was hot. It's a wonder that somebody didn't really get hurt in that situation. Swimming around boat docks is not a good idea. Okay, how we doing on time? We've got a few minutes. This is the most common utility supply in the U.S. is a multi-grounded neutral system, and it comes under criticism because they're putting energy in the earth at every house at the pole. Here's a little schematic of it. Here's the transformer on the pole. It's grounded at the pole. Utility transformer. There's the ground. It's the same as this. Then it's grounded at the house at your riser. So we're introducing a lot of current into the ground with this system, but it's what we got and what we use. I'm gonna skip through a couple of these real quick. That's the ground at the pole from the transformer. Okay, current will take all available paths, not just the path that is designed to. It'll take whatever path's available. And when there's a fault, it'll go on any conductive material. That's why we bond to eliminate these unintentional paths. Go through this real quick. This is a call out I got on. This was a squirrel had chewed through this. This is right after it had been repaired, but he chewed. They like to chew on that aluminum neutral, bare neutral, and he chewed it in two. So this home lost its neutral, service neutral to the house. As an older house, the underground water pipe was still there, but when the plumber put in the PEX, down below here is actually the old water pipe. If he just left it connected to that, he would still have a grounding electrode, but he took it loose because he was a plumber. The only return path for that neutral current back to the transformer was on the coaxial cable. That's what's left of it. It was traveling on that shield that was carrying all the neutral current of that house back to the transformer, and it melted it down, and it's a wonder it didn't burn the house down. That's where the coax ran up and went into the side of the house on this log house. Very dangerous situation. That's not really to the grounding, but it's showing what it's taking another path. It's going to take whatever path is there. The only path there was that coax. Okay, when parallel paths are available, it'll divide between these paths. And depending on the resistance and conductivity of those paths is how much goes on each one. Now, look at this one. This is a sub panel in a house. Just kind of look at it like you're doing an inspection. Does anything jump out at you other than the state of Tennessee approved code inspection? He said everything was good here. Okay, like I say, this is a sub panel, 4-wire feed. See where they landed the equipment grounding feeder? It's right there with the neutral. It was supposed to be right there. That's where your equipment grounds. The equipment grounds were in the proper place. The neutrals were in the proper place, but there's no path back to the breaker that's feeding this panel because this should have gone here. See that? I took some amp readings on this particular panel with a load on it. There's 7.3 amps on that bare equipment ground feeder. It's going back from the breaker that's feeding that sub panel. Very dangerous. That same current's on that metal can. If you touch it, everything that's bonded in that system is getting that current on it. Here's the neutral, same load. The reason there's more current on that neutral than there is on the equipment ground. See the difference in the size of the wires? More current's going to go on the more conductive wire. So that was a, what's that, 11, 18, almost a 19 amp load. And over a third of it is traveling on that bare equipment ground. Very dangerous. And that's something that if you're not paying attention, you can miss that real easy. The code inspector did. So look closely at these things. Just kind of take your time and do what I call a macro view. Do a micro view and a macro view. Micro, you're looking up close, and macro, stand back, kind of look at everything. Have we got a few more minutes? We're
running down the wire here. How much time? How much more you got?
If I can get another 5 minutes, is that okay?
I think we can do 5 more minutes.
Okay. I wanted to show this real quick. This is a little sub panel. This is the neutral bar. The bonding jumper has been pulled back. In my opinion, it should be taken off to avoid mistakes. But anyway, it's not connected. So this is properly wired. Okay, I put a load on this panel. This is just a little experiment I did to show some things. Put a load on it. This is the service neutral. It's about a 16 amp load on this 20 amp branch circuit. That's the only thing on right now. And that's showing that the neutral is carrying that 16 amps back to through the feeder, back to the supply breaker. Now, still I'm checking the equipment ground, no current on that equipment ground, as it should be. There should be none on there because it's not bonded and they're separated. That's the way it should be. Okay, so now I go in here and I hook it in, I bond it. Same load, read on the service neutral. Now I've dropped to about 10 amps on this service neutral. Well, where'd it go? I still got the same load. There it went. Now it's taking that parallel path back because this sub panel is bonded. That's what happens when they're bonded. So this metal enclosure, all these equipment grounds, this service, bare wire, and this SE cable, they're all energized, carrying current. Dangerous situation. This is a grounding electroconductor at a commercial property that's got 12 amps on it. That's deadly. This one had a compromised neutral, and the neutral current was taking an alternate path, the best path it had, back to the transformer. This conductor went into a ground rod that was in a concrete slab full of rebar. The power pole with the transformer was at the corner of that same slab, all that rebar. So it had a good path back to the driven rod at that pole. Now, I've had home inspectors tell me that when they check a grounding electroconductor, they'll give it a tug to make sure it's good and tight. Guys, don't do that. If you had pulled this one loose, that 12 amps is going through you to the ground, and you're going to die right there. Equipment grounding electroconductors can kill you if there's a fault on them, because they will carry current when there's a fault. So don't be pulling on those guys. Now, this is another grounding electroconductor. This is a normal situation. Even though you don't want any current on that, it's still a parallel path because they're bonded at the service equipment, and it's going through the ground back to that transformer. So you're going to get a little bit of current on it. I mean, there's going to be some measurable current on it if there's a load on that house. This is 200 milliamps. Now, if you put some kind of load like a person, it's going to drop it because there's more resistance, but there will be some load on it because there's a parallel path. It's not a perfect system. Okay, when there's no path to clear the fault, the voltage will rise to the energizing level, or the energized voltage level. This is a sub panel. You can see it's a 3-wire feed. This is a floating, not bonded. This was energized. A hot wire had gotten, this was all metal barn. Hot wire had gotten on a fluorescent light against the can of the light. It was all in conduit, and it energized everything in this building. I had 118 volts from this metal siding on this building to a ground rod, to the neutral. Wonder if somebody didn't get killed in there, and it didn't have any path to clear that fault. Okay, here's a little checklist of accessible components. Identify all visible and accessible electrodes. Confirm the presence of the grounding electroconductor, proper protection, proper size. Confirm bonding of the neutral at the service equipment, and confirm bonding of metal water pipes and all metal enclosures and equipment. Confirm the separation of the equipment ground and the neutral at downstream panels, sub panels, anything downstream of the service. And ensure that neutrals and equipment ground are properly color identified. Confirm the presence of the intersystem bonding terminal at all newer installations. And I think that's all I've got. If you've got some questions, we'll.
Quick question, Mike.
Yes, sir.
Do you advise using a meter to check the conductors to see if there's load on the ground?
Using a meter?
Yeah.
That's a good question. That's a personal choice. I actually teach a class testing electrical systems. Some guys, it's definitely not a requirement for a home inspector. I do it. I'm an electrician. I'm gonna do a little more in depth, but if you're gonna do it, get proper training. I'd say that. Some guys go out and buy a multimeter, and you need to know what you're looking at and when to check and what to check. So it's a good thing to have. like I say, I always tell people if you're comfortable reading just the voltage at the service equipment, read the incoming voltage. It's going to tell you a lot because there are 208 single phase services out there, and a lot of guys are just blanket putting in their reports. The service is a 240, 120 volt service. You will not know what it is unless you measure it. You can't tell visually by looking at it.